Welcome to Study Loop.
Okay, so the magnetic field that is perpendicular, um, it produces an acceleration perpendicular to the direction of motion. So this is given by the force that causes this acceleration is given by ma perpendicular, a perpendicular being the perpendicular acceleration, and so that will be equal to the magnetic field force from the magnetic field, QVB. Therefore, acceleration, perpendicular acceleration, will be QVB over m. So now we use an equation of motion, if you'll remember one of those things. So we're going to use distance, d perpendicular, this is the deflection distance we want to find, will be equal to initial perpendicular distance, which will be 0, plus initial velocity perpendicularly in the perpendicular direction, v naught perpendicular times t, and that will be 0, plus 1/2 a perpendicular times t squared. So this is an equation of motion to find perpendicular distance using perpendicular acceleration, and so we're left with 1/2 a perpendicular times t squared. So plugging in a perpendicular, you have 1/2 times qvb over m times t squared. And so this is qvb over 2m times t, which is L over v, the length traveled over velocity, and you square that. And so plugging in values, you have charge, which is 18.5 times 10 to the negative 9 coulombs, times velocity. And so let's simplify this a bit further. You have QBL squared over 2mv. Right. So magnetic field strength B is 5 times 10 to the negative 5 Tesla. And L is 1.5 times 10 to the 3 meters, 1,500 meters, or 1,500 meters. You square that, and this will be over 2 times m, the mass, which is 3.4 times 10 to the negative 3 kilograms, times velocity, which is 155 meters per second. This will give you, as a result, this will give you a perpendicular distance of 1.97 times 10 to the negative 6 meters. So a very small, 1.97 micrometers is a very small distance. So therefore we can in fact consider this to be we can in fact make the assumption that acceleration is constant.